questions and answers. So again, I'm Oliver Gunasekera. I'm the CEO and co-founder of Impossible Metals. So let me share my screen. Yeah, so Impossible Metals is a company that is headquartered in Silicon Valley in North California. And our mission is really to deliver new technology for the harvesting of polymetallic nodules. These are the potato-sized rocks that form on the seabed floor. And we've designed our vehicle basically to try to minimize the environmental concerns that many have with the traditional approach, which I'll cover in the presentation. So here you can see me on the right with my co-founder Jason. This vehicle that we're standing on is an underwater vehicle. So it can go about 4 kilometers deep. In fact, it can go up to 6 kilometers deep underwater, and it is fully autonomous, and it's designed to pick up or harvest the polymetallic nodules. But let me start by talking about why do we think there is a problem. And I think if you look at the demand curve put out by the International Energy Association, we need huge quantities of critical metals, specifically nickel. So this red line on this graph is the predicted growth that is needed for nickel. And the blue is kind of the existing land-based mines. The yellow is probably new land mines that are likely to come online. And the green is the recycling. So you can see here, recycling is going to be important in the future, but by 2040, it's maybe about 10% of the demand will come from recycling. And so we have this big gap. How are we going to fill this gap? And this gap is caused because of the energy transition, because we need to build new infrastructure, because we need defense, and more people want better lives. And so that drives demand for these metals. So the question is, how do we fill this gap? And as you can see, the gap is starting. And it's not very long until the gap becomes quite substantial, like 1 million metric tons in 2030. The other challenge is that the environmental impact of land-based mining is not so great. You have often big open pit mines, you have a lot of environment and biodiversity, and potentially sometimes people displaced. And there are a lot of social impacts. You know, we do know that sometimes teenagers are used to do mining. There are people forced off their land. There is pollution from the mining operation. So the question is, how do we get this metal without all of these environmental and social challenges? And how do we get this metal at the right price? Because what normally happens in mining is that as the supply gets tight, the price rises. And as the price rises, more mines come online. And that's okay. But if we want everyone to be able to afford newer technology, electric vehicles, air conditioning, then we don't want the price to get so high. And so bringing online a new supply of minerals that won't drive the price up, that won't potentially impact the environment or the social life of people, is really the mission of Impossible Metals, and is what we think we can do with seabed minerals. So we've identified a gap, and I think there are really 2 choices. Do we do seabed mining, or do we try to accelerate and do more land-based mining? And if you look at these 2, it takes a really long time for land-based mines. It averages now 18 years globally from finding a deposit to getting all the infrastructure built to actually starting the mine. Whereas in the ocean, we think that can be done in a much shorter period, in around 6 years. And in fact, there are many companies that have already spent 10, 15 years doing environmental work that we can partner with. So we can get to market a lot quicker. Secondly, if you look at how much material is there, well, there is 3 times more nickel in the ocean and 12 times more cobalt. And that's because the ocean is large. It's 71% of the planet. And we have not yet mined. So the problem with traditional land mining is that it's in that 29%, which is our countries. But we've been mining for a long time. So the amount that's available is actually quite low. Also, for the West, for Europe, for North America, China controlling many of these mines is a strategic problem. And so the West really wants to have an independent source that is not directly controlled by China. And now if we look at cost, it averaged for a nickel mine last year just under 15,000 US dollars per metric ton to do the mining and the mineral processing. And unfortunately, the market price was around $15,000. And so many mines had to close because they could not make money. But the seabed has some really big advantages, which I'll come on to. It's a huge resource. You have 4 metals in one. You don't have to tunnel or blast. You don't need to build infrastructure. And as a result, it will be much less expensive. With the traditional technology, it could be 5 times less expensive. With our autonomous technology, our robotic technology, we're estimating it to be 20 times less expensive. And then the environmental impacts, which I'm going to talk more about. But on land-based mining, it's well understood, those impacts. But the deep ocean is thousands of miles away from any land. It's up to, say, 4 to 6 kilometers deep. There is no people living there. So you're not going to have impacts on people and communities. Now, there is an environment, but that environment has very little life compared to the life that we find in rainforests. It's special life, it's unique life, it needs to be preserved, but by the start, there's a lot less of it. And so that's why I think there's an opportunity to do something that is significantly better. But what I'd like to now talk a little bit is our technology. So this video here on the left is the traditional approach, what we would call crawler and riser technology. This technology was first tested in the 1970s and is basically what most of the industry is pursuing. It's a big machine that gets lowered to the seabed floor, and it basically vacuums up, it sucks up the nodules and pumps them up a riser system to a production support vessel where the water and sediment is separated and pumped back into the ocean. Some of the challenges with this is that it does require a lot of capital. It has a high CapEx and OpEx model. It will destroy any life that is in front of the machine. And we're not sure it will have great reliability because it's a tethered system. It will be hugely affected by the weather in the ocean, the sea states, the size of the waves. And as a result, we think it's not going to be as efficient as our approach. Now, our approach is radically different. And it's designed to be low and scalable CapEx. We can start with a small number of robots and then increase the number. And it uses computer vision and AI to preserve the marine habitat. And because it's a parallel fleet, we believe it will be far more reliable and have much higher uptime. Now, what I'd like to do is play the video. It's about a 60-second video. It has audio that describes how our system works. So let me play that now.
At Impossible Metals, we are developing autonomous underwater vehicles that are launched from a ship to the ocean floor, where there are vast fields of rocks, called nodules, that are rich in metals that are critical for low-carbon technologies, like batteries. Hovering over the ocean floor, artificial intelligence uses cameras and robotic arms to pick up each nodule individually, minimizing sediment disturbance and avoiding visible life, while leaving behind a percentage and pattern of nodules to preserve biodiversity and ecosystem services. The collected nodules are stored on board, and once the vehicle is full, it returns to the ship. The recovery crane is designed with motion compensation for fast docking, giving the vehicle a stationary target. Once on board the ship, nodules are offloaded and the battery is swapped before the vehicle's next trip to the seafloor. A key part of this system is that the fleet of underwater vehicles remains at sea. As one ship is filled with nodules, another arrives to continue the collection operation. Our highly scalable fleet is designed to reach the high production levels required to meet market demand.
So the fundamental of this system is that it's using a fleet of autonomous underwater vehicles, underwater robots. And so there is no tether. There is no landing on the seabed floor. There is no riser system that you see here with the competing solution. There's no production support vessel. There's no dewatering. There's no return plume. So it's a very different system that's really only possible with 21st century technology of semiconductors and robotics, AI, batteries. And you can see here, our vehicle doesn't land, it hovers. It puts the material inside the vehicle and moves up and down the water column. And we reuse the transport ship to actually launch and recover the vehicles. That avoids the cost of needing this dedicated production support vessel that you see here. So this ship is removed in our architecture because we don't have a dredging machine, we don't have a riser system, we don't have a discharge plume. We just have the transport ship, which is shown here, and our vehicles. Now, let's talk a little bit about the environment and how we're trying to preserve the habitat. I think the first thing to show is that when we look at how much life exists in the deep ocean, it's technically called the abysmal zone. It's between 4 and 6 kilometers deep. It has very, very little life just that exists there. It's a low energy environment. There's no light from the sun that reaches these depths. There is life, but there's orders of magnitude less life than what we find in other areas like tropical forests, where we get the majority of our nickel and cobalt from today. So before you do anything, you're comparing a rainforest, which has huge amounts of life that you have to destroy to get at the nickel below the rainforest, with an environment that has much less life. That, I think, is already a good start. The next step is, in the design of our technology, we've gone to great lengths to minimize the primary concerns that the environmentalists have. Now, these nodules, I'm actually holding one up here, these are potato-sized rocks. So they form over millions of years, and they just lie on the seabed floor, as you can see in this picture here. And what we need to do is to pick them. Now, instead of landing the vehicle, we have a vehicle that is hovering. It doesn't land, it doesn't touch the seabed floor, and it's using its cameras to look at the seabed floor and look for life. If we see life, as you can see in this animation here, 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 we won't disturb it. If we see a deep sea coral or a sponge, we will put a quarantine area and the vehicle will fly over the top. Because we don't have tracks, because we're not injecting water, because we don't have a riser system with a discharge plume, we have very little sediment disturbance, vastly different than what you would see with a traditional system. And one of the things that we have programmed our AI to do is to leave 60% of these nodules undisturbed by default. So we will prioritize the larger nodules and the ones that have life on them. So some of the nodules, depending on the location, maybe 1% of them have a deep sea coral or a sponge. We know of a species of octopus that lays its eggs. The AI vision system will detect this and say, okay, I'm quarantining a circle around this area. I'm not going to disturb it. I'm just going to fly over the top. And that will be part of the 60%, because all of the nodules have life. They have bacterial life, they have microscopic life. Our cameras can't see things that are below 1 millimeter in size, but we will always leave 60% behind. This is our life detection algorithm. So this is from our robotics lab. And you can see that the camera is identifying the nodules, the rocks in red, but it's also identifying the life and putting a green circle. And so anything in the green circle, we would not disturb. And the way that our life detection AI algorithm works, first of all, it runs completely on the vehicle. So we have a very powerful NVIDIA graphics processor chip in the vehicle. We have stereo cameras, and that's the image that you're seeing. And this algorithm to detect is running on the vehicle. Now, the algorithm, the AI algorithm, is looking for three things. It's looking for the seabed, it's looking for the nodule, the actual rock we want to pick up, and then it's looking for anything else. And we assume anything else is life, and hence needs to be avoided and left undisturbed. This avoids us needing to identify and previously see the type of life. So we look for seabed, we look for nodules, and anything else. So we don't have to have previously seen what type of life it is. And our vehicle will just identify it as long as it's bigger than 1 millimeter or so. And the vehicle will fly over the top, put a quarantine green circle around it, and anything in the green circle will not be disturbed. That's in addition to the 60%, will be part of the 60% of nodules that we don't disturb anyway. So when we started the company, we were very aware of the environmental concerns that are raised with the traditional approach to deep sea mining for nodules. And we put together a strategy of how we could design technology that would minimize the impact. So there was a concern that if you remove all of the nodules, what about the octopus that lays its eggs on the nodules, or the corals, the deep sea corals that need the nodules to attach to? Well, this is the strategy of selective harvesting and leaving 60% behind. What about the biodiversity? We know it's very special. You don't have to go many kilometers away and you will find different species of bacteria, of the small microorganisms, and even the larger megafauna. And so again, using the AI cameras to detect that life and leave it undisturbed, leaving 60% behind. The plume. The plume is a big concern. People are concerned that the plume could travel for long distances, especially the midwater plume. It could impact the fishing stock by impacting the plankton, which is then ate by the fish. So we have gone to great lengths to minimize any sediment disturbance. As I said, our vehicle is hovering, doesn't actually touch the seabed. It's designed to hover and pick up the nodules. And we don't have tracks, we don't inject water into the seabed, and we don't have a discharge plume. So we will have a little bit of disturbance as we pick, but it will be significantly less. Noise. Most of the noise concern is actually at the surface or close to the surface, because it's the marine mammals, the dolphins, the whales, the sharks that are affected by noise. And one of the biggest sources of noise is actually the ship. And so by avoiding having a dedicated ship, avoiding having a riser system with pumps, by avoiding the need to have dynamic positioning, which is technology on ships to keep the ship very, very still by using big thrusters that make a lot of noise. We don't need that. All of that will significantly reduce the noise footprint. Light. We do need a little bit of light. It is pitch black, and we need light to be able to see. So we will turn the lights on only as we get to the seabed floor, not as they move up and down the water column, which is the majority of the time in the water. But we will also work and are working with marine scientists to optimize the wavelength, the color of the light that will have the least impact. And we're looking at adopting new image sensors that have very, very low light performance, meaning you don't need to use a lot of light. If you've looked at your phone, phones have got much better at taking pictures in the night time. And that's because the sensor technology has improved. That's something we can leverage. And then finally, greenhouse emissions. We, I think, are the only mining company that has committed to be net zero, meaning we will have no emissions from our mining, transportation, or mineral processing operations, carbon emissions. We will either do that by using new technologies, or we will use carbon offsetting to offset any emissions that would be generated by our operation. And that's a commitment that we've made, again, very, very unique. And that is for the actual harvesting of the robotic fleet, the transportation of the ships, and the mineral processing. A lot of the design of our vehicle and how we test have been influenced by scientific roundtables. So we've held now 4 of these. This is where we bring together a group of marine scientists to help answer technical questions on the development and testing of our technology. And we publish the report from those meetings. It lists the scientists that volunteer their time, and also any conclusions that are reached, and those are available on our website, and we will continue to do this as we progress. And so a lot of the design of our technology has been heavily influenced by this very valuable scientific feedback that we've received. We have done a little bit of ocean testing. We have done 2 ocean deployments last year. The most recent one was the one we did off Florida. We went about 100 miles within the US exclusive economic zone off the coast of Florida. And I have a very short video from maybe I have a video. Let me see if I can play it. Yeah, so this is just showing the drone footage. You can see our vehicle on the ship. This is just before we were about to deploy it. And this allowed us to test the vehicle at about 2 kilometers depth, fully autonomously, untethered. So really proving the key capabilities of the vehicle. So we've actually had a lot of technical progress. You know, what you can see playing here is the video of Eureka 2. This is some testing that we do in the harbor. You can see all 3 of the arms operating. There is a little bit of sediment disturbance. We've really optimized the speed and accuracy of the arms. And in the future, we will optimize the pick position to minimize the sediment. Right now, we're scraping a little bit the seabed. But this comes on the back of Eureka 1 and even the Delta arm. So the first thing that we built and tested in March of 22 was this unique robotic arm that you can see operating on the vehicle. And we did that in the lab, and that was to really show that we could operate an arm quickly and control it with a camera. The second thing we built and concluded was in May of 23 was Eureka 1. So this was a complete vehicle, but it was designed for shallow water, for testing capabilities. It did have a buoyancy engine, it had the arm, It had the computer vision and AI, but was only rated at 25 meters and had just a single arm. And Eureka 2, as you can see here, is rated at 6 kilometers. It has 3 arms, but it still has a relatively small payload. So it's not something that is viable for commercial operation, but it proves all the key technology. What we're working on right now is the production size system, is what we call Eureka 3 and 4. So this takes the Eureka 2 vehicle and makes it larger. And what we do is we keep the depth rating, but we increase the payload capability from 100 kilograms to 4,000 kilograms. So this is something that we can now deploy commercially. We've increased the number of arms to 12. It's obviously a much bigger vehicle. It's actually, the Eureka 3 is the size of a 20-foot shipping container. And it has a fairly large battery on board, so 135 kilowatt hour. That's like 2 Tesla Model 3 batteries or 1 big truck. So fairly large battery, but we estimate costs will be under $2 million. And the goal would be to use a fleet of these to deploy. Now, in parallel, we're also looking at Eureka 4. This is an even larger vehicle. You can think of it as a 40-foot shipping container vehicle. It has more arms. It has a bigger payload. It uploads the payload to 12 metric tons. But that has the advantage of driving our costs down even further. Now, another big benefit of our system, in addition to the economics, well, that supports the economics and the environmental, is really the operational advantages. One of the big benefits here is that we can actually access more of the resource. Because if you're using a traditional dredging crawler tractor with a riser system, then you can't really operate on very large inclines. You need very, very flat seabed. We don't have that restriction. We also can avoid the holes. We are hovering. The big track vehicles would get stuck in some of the holes in the ocean. And we can operate in a wider range of sea, weather, and sea states. So that ultimately allows us to access more of the resource. As I've mentioned, it's very much a parallel system. There is no single point of failure. So we have a parallel fleet instead of one vehicle. We have the ability to operate in a wide range of sea states. And so that, we think, will again increase our uptime. The problem with the dredging system is that if the collector fails, the riser fails, the dewatering fails, everything stops, and it will potentially take many days, maybe even weeks, to recover and repair the system. So a lot of downtime, and you can't operate in a wide range of weather conditions. Finally, in our architecture, we avoid this need to do a ship-to-ship transfer. So in the traditional approach, you have your production support vessel, but it only has storage for a few days. So every few days, you have to offload the nodules that you've collected to a transport ship. And that's complex. You need to do that on the high seas. You need to do that safely. But not only do you need to transfer the nodules, you need to transfer crew and personnel, fuel, supplies. All of this gets complicated and will not operate in a wide range of sea states, and potentially could result in a break in production. So we avoid all of this, and we think this is something that is going to be pretty expensive to actually get to work correctly. So on the economics, it's something we care a lot about. I mentioned that we are looking to be something like 20 times less expensive than the average mine on land. And this is both for the mineral processing and the mining. And anyone going after deep sea mining is probably going to get a 5x benefit, even if they're using the older dredging technology. And the reason they're going to get the 5x benefit is because these nodules are high grade, they're 4 metals in one, and you don't need any new transport infrastructure. The problem with new mines on land is that they're always very remote. They're typically very low grade. And so you have to remove huge quantities of material, typically below rainforests, and you have to build roads and railways and power connections and accommodation and infrastructure for workers. All of that adds a lot of cost. In the ocean, we just reuse the ships and ports. We don't need to build roads and railway lines, and that has a massive cost saving. We go further because of our unique technology, because we don't need a dedicated production support vessel, all of that CapEx and OpEx. Typically that vehicle, that ship has 130 people working on board. All of that is removed in our architecture. We just reuse the existing transport ships, and we've fully automated our system. We basically need very few people. So the robots, the cranes, these are all automated. The battery swap, the payload empty, it's all automated. So we need far few people. And people on the ocean are at least 10x the cost of people on land, because you have to pay for the floating hotel that basically supports them. So by avoiding people, you have a massive cost saving. So we're estimating for a Eureka-free system, we're going to be about $743 for the all-in sustaining costs for a metric ton of nickel. That's processed, that's transport, and that's mined. So all of the operations being about 20 times less expensive than the average nickel mine last year on land. Coming to the end here, one of the things we've started to think about is how do we scale? And obviously we are a parallel system. So if we wanted to get to, let's say, 2.3 million tons of dry nodules per year, we have a major advantage that because of our architecture, without a tether, without needing DP, we can operate in a wide range of sea states and weather conditions. So we're estimating we can operate in 325 days a year out of 365. Our competitors are talking about 216 because of the architecture that they have with a physical tether and a riser system connected to their vehicle. That has a massive advantage. We also, as I've mentioned, we don't need and don't have the production support vessel. So if you're familiar with the Hidden Gem, the ship that the metals company has deployed with its crew of 130 people, we don't need that. That doesn't exist in our architecture because we're reusing the transport ships to launch and recover the vehicle. We don't have a riser system. So that riser system that has to go the 4 to 6 kilometers, all the energy, all of the noise that is consumed, the dewatering, all of that is not required because the nodules go inside our vehicles. And of course, each of our vehicles has less capacity than one dredging tractor, but it's parallel. So we would deploy about 194 Eureka 3s to achieve 2.3 million metric tons. So again, that still comes out, as you saw on the previous slide, to be about 4 times less expensive when you factor in the CapEx and the OpEx, even though it's a bigger fleet. So my last slide, and then I'll open up for questions. What we've tried to do at Impossible Metals is come up with a technology solution, a 21st century technology solution that is environmentally responsible. It really uses state-of-the-art computer vision, AI, robotics, batteries to minimize the environmental impact. And I want to say minimize. There's always going to be some impact, but we are doing everything we can to minimize it and have significantly less impact than what you would have on land, and especially very, very little or none social impacts. We've built a system that is going to be very reliable. it has redundancy. It has no single points of failure. It can operate in a wide range of sea states and weather conditions. So it's going to be very, very reliable. And then third and finally, we've put a lot of effort to drive the cost down, to minimize the time that we need for collection, to avoid having a dedicated ship. And that, in our view, will be 20 times less expensive than land mining, 4 times less expensive than the competing dredging tractors with riser systems. So with that, I would like to say thank you. Very happy to open up to any questions. If you want to follow the company and get updates, then LinkedIn is probably the best way to do, with the QR code or with the URL that I've put here. So thank you. Happy to take questions or continue the dialogue. Yeah, please go ahead.
Hi, my name is Brume. My question borders on your environmental impact. Given the limited knowledge of deep sea ecosystems, how is the precautionary principles applied to the use of the AUVs in exploration or mining activities? Also, what long-term monitoring obligation exists to detect and respond? Can you hear me?
Yes, I can.
What long-term monitoring obligation exists to detect and respond to delayed or cumulative impacts on biodiversities? And lastly, if an unforeseen environmental effects from the AUV's deployments are detected, are there adaptive measures in place to halt or modify operations? Thank you.
Yeah, great questions. Let's take one at a time, and you may have to repeat the question so I get it. So I think the first question was about the precautionary approach. So you know, we've had a moratorium for 60 years. There is no deep sea mining happening today. We've been researching and studying, and you know, deep sea mining is highly regulated. So if we take the ISA, the International Seabed Authority, set up by the UN Law of the Sea, it has awarded around 30 exploration licenses. One of the requirements of the exploration license is to do the marine science. You have to do a very extensive environmental impact assessment. You have to commit to a 5-year work program. Typically, you have to spend $50 million or more over the 5 years collecting the scientific data of what is the environmental baseline. You then have to write that up in an environmental impact statement, which will ultimately be submitted to the regulatory body, and then they will make a decision of whether the mining is approved or not. And so this is the first time an extraction industry is contemplating starting, where we have a very, very high bar of environmental stewardship that has to be done prior to the environment. And we know a lot. So as I said, for 60 years, we've been researching this area. Each of the 40 or so licensed areas that have an exploration area has been collecting data. Collectively, I think about $2 billion has been spent, and all of that data has been submitted to the regulatory bodies. There's a deep database on the ISA, for instance, and I think something 90% of science in the deep ocean has been funded by deep sea mining companies. And so the precautionary approach, I think, is what we are doing. Our vehicle is designed to only take 40% of the modules, to look for life, to avoid it being impacted. Second part of your question, I think, was about the monitoring. As part of any exploitation application, you will have to commit to a monitoring program. And so there will be extensive monitoring being done as the mining operates. There will be obligations to report on the mining operation, and if there are any abnormalities of deviations from what you committed in your environmental impact assessment, those would have to be communicated immediately to the regulatory body, and they have the ability to cause you to stop immediately if there were impacts that you had not documented that are being occurring. I also want to mention that if all of the deep sea mining happened and it supplied all of our future needs to 2040, we're talking about a fraction of a percent of the seabed that would be impacted. It's a relatively small area compared to the size of the ocean. And obviously, if we don't do this, we continue to cut down rainforests and destroy biodiversity. But also, I think we won't achieve net zero. The metal prices will just get too expensive, and the deep ocean will be hugely impacted by temperature rise and climate change. So hopefully I answered. Let me know if there's any parts of the question I didn't answer, and I'll try and answer those. Please go ahead.